We'll continue in the series Our Place in the Universe, this time looking at our galaxy. And here are some important ideas. Now, a galaxy is a huge collection of gas, space dust, and billions of stars and their solar systems, all held together by gravity. So here we have a planet, and a planet may be orbiting a star, and we call that a solar system. But a solar system is just one component of a much larger organization of solar systems that we call a galaxy. Now, this is a picture of a spiral galaxy, much like our Milky Way galaxy, but it's not our own because we wouldn't be able to have a picture of our galaxy. We're in our galaxy. But the Milky Way is about 100,000 light years across, so it would take light 100,000 years to go from edge to edge. It consists of several hundred billion stars gravitationally bound together, and the spiral arms rotate around the core of the galaxy. The spiral arms are the concentrations of stars, and our sun would be about 26,000 light years from the core of our galaxy. Now let's take a look at an animation of what a galaxy looks like. So all the little points of light would be stars. Any planets they had would be too small to see in this animation. It takes about 250 million years for the sun to orbit the core of the galaxy. Now, if the sun is here and our solar system is here, when we look up at the night sky, of course we see stars, but when we look in a certain direction, we see that band going across the sky, that kind of bright band called the Milky Way. That's when we're looking towards the center of our galaxy. And with a camera, you can capture this kind of image. So this is the Milky Way. We're in a spiral arm looking towards the core. So here's the core of our galaxy. Now the stars over here and the stars over here are looking away from the core of the galaxy. But when we look towards the center, we see this concentration of material. Now again, our sun is in a spiral arm here, and most of the stars in the night sky are neighboring stars. They're just sort of near our sun. And here we see some of the names of some of the close by stars to our sun. And let's remind ourselves also that stars are giant spheres of hydrogen gas. They're not pointy like this. Now let's take a look at the relationship between our solar system. So here's a picture of our solar system. Let's put that in its place in our Milky Way galaxy with another animation. So here we see the Milky Way. So they've shown us some of the movements of the planets in a plane. Our sun. And now we zoom out to see the plane of our solar system. So here we see then that the plane of our solar system is at an angle with respect to the plane of the Milky Way. So here's a more complicated diagram, though, showing the Milky Way. There's the plane of the Milky Way, and our Sun and our solar system. The plane of our solar system is at an angle with respect to the Milky Way. Now, when we look at the Milky Way, we see bright areas and dark areas. The bright areas are the combined light from millions of stars. It's just that the camera used here can't distinguish each individual star, so we just see it as a bright patch. The dark areas are gas and space dust. So it is opaque to light, so the light gets blocked by the space dust, so we can't see stars behind these dark regions. The light is being absorbed by the dust. Now, when we say space dust, we're referring to tiny particles of matter smaller than a grain of sand, often bits of rock or carbon-rich soot-like grains. And it can also include frozen water, little ice particles. So these materials, the space dust, is composed of heavy elements made in stars and ejected back into space, where they bonded together to form small molecules. And those molecules can assemble into larger grainy structures. And that's the stuff that is blocking some of the starlight of stars behind the space dust. Now, space dust is not the kind of dust you find in your home, which is composed of a lot of dead skin cells along with other particles in the air that have settled on your surface. So the space dust, that's the raw material out of which to make new stars with planets. An example of this can be found in the familiar constellation Orion. So here we are at Joshua Tree, and we've got Orion in the top right. We've got 1, 2, 3, the 4 stars that are the boundary of Orion, and we have Orion's belt here, those 3 stars, and then the sword of Orion. Let's zoom in on that sword, and that's where the Orion Nebula is located. So here's a picture of the Orion Nebula. It is a bunch of gas and dust illuminated by stars in the nebula. And a nebula then is a giant cloud of gas and dust, and previous generations of exploding stars have enriched the nebula with heavy elements. The material in a nebula can be incorporated into new stars and planets. But where exactly is the Orion Nebula? Well, let's take a look at this drawing of the Milky Way galaxy. Of course, it can't be a picture because we're in the galaxy. We wouldn't be able to get out of it to take this picture. So this is a reconstruction, but it is intended to be fairly accurate in the locations of celestial objects. Now, here's our solar system in one of the spiral arms, and here's the core of the galaxy. Now, down here, we see the Orion Nebula then. Again, our solar system would be here, so when we're looking at Orion, we're looking away from the core of the galaxy, so we won't see the Orion Nebula set against the backdrop of the Milky Way. On the other hand, consider the Lagoon Nebula. Here's the Milky Way, and the Lagoon Nebula is this pink and purple splotch right there. Well, again, let's situate ourselves. Here's our solar system, and here's the core of the galaxy. If we're looking towards the core, we're going to see the Milky Way. And in fact, the Lagoon Nebula is right here. So we see the Lagoon Nebula as we look from our solar system towards the core of the Milky Way. We see the Lagoon Nebula in the pathway. And that's why then we see the Lagoon Nebula against the backdrop of the Milky Way. We're looking towards the core of the galaxy, and the Lagoon Nebula is between us and the core of the galaxy. With the Hubble Space Telescope, the Lagoon Nebula looks like this. Here's the Trifid Nebula, the Carina Nebula. Here's a wide-angle shot of the Orion Nebula, and nearby is the famous Horsehead Nebula. Through the Hubble, it looks like this. So this cloud of gas and dust has the material to make 30 suns, with planets orbiting those stars. This image was combined with some other telescopes, a new image from the Hubble and these other telescopes, capturing some of the light in the infrared region of the electromagnetic spectrum. Beautiful picture of the Horsehead Nebula. Here we see the Eagle Nebula. It's about 7,000 light years away. It's sometimes called the Pillars of Creation. These giant, massive structures are giant clouds of gas and dust. The distance across one of the pillars is about 5 light years. Now they're illuminated by nearby stars, and new stars, they generate stellar winds that can move at around 10,000 miles per hour. So high energy particles are bumping into the gas clouds, and that can actually cause the clouds to sort of weather, to sort of dissipate. It may be that these pillars no longer exist as we see them today. Because remember, we're seeing these pillars as they were 7,000 years ago. In 7,000 years' time, the stellar winds may have disrupted these pillars. They're called pillars of creation again because the idea is these giant clouds of gas and dust are the raw materials to make new solar systems. So wherever there is gas and dust, new solar systems can form. However, scientists believe that the rate of new star formation is decreasing, and this means that most of the stars that will ever exist are already born. That's metaphorical, already shining light. In a sense, galaxies are running out of gas to make new stars. Scientists estimate that around 1 billion to 3 billion years after the universe began was the highest rate of star formation, and it's been decreasing ever since. Now, when we look up into the night sky, then, as we peer towards the Milky Way, we see all these other stars. They are also in the Milky Way, but we might be tempted to ask a profound question. How many of these stars have planets? And only recently, in the last couple decades, has an answer to that question been achievable. To get an answer to that question, consider the following. This picture was taken on November 11, 2019. It's our sun. If you'll notice in the top right, there's a little spot there. Let's crop in. We see it better. That spot is Mercury. So Mercury, in its orbit around the sun, positioned itself between us and the sun, and so a picture can reveal Mercury against the backdrop of the sun. This is called transiting, the transit of Mercury across the face of the sun. Well, if we think about it then, planets that are orbiting a star would temporarily block a tiny fraction of light from that star. So if we were measuring the amount of light coming from our sun and Mercury goes on by, it's going to be blocking some of the light from the sun. It will be a tiny fraction, but if we could detect that, then we could detect the presence of planets. And that's in fact what scientists are trying to do when they're searching for exoplanets. An exoplanet is a planet orbiting another star. And the idea is NASA has sent up satellites that are taking pictures of stars, measuring the luminosity, the brightness of stars, and they're looking for moments when the brightness of a star is diminished a little bit. And that could be an indication that a planet is moving in its orbit between the camera and the star. So NASA launched orbiting satellites. The most recent is called TESS, for Transiting Exoplanet Survey Satellite. Again, when the planet is orbiting, it's called the transit, when it's between the star and the observer. This is a recent picture of some of the TESS survey data. So these are all the regions of the sky that TESS has been taking pictures of. So here's the Milky Way and the large and small Magellanic Clouds. And what TESS does is it takes pictures of many stars at different times to see if a star's light gets dimmer, then brighter, then dimmer again. And a periodic reduction in starlight would indicate an orbiting planet. And not long ago, scientists released this type of image here. This curvy thing here is the Milky Way, and all these little circles are stars where there is evidence that those stars have planets. In other words, lots of stars have planets. Because the scientists have only been searching for some years now, and already thousands of stars have been detected that have planets. And at this point then, scientists estimate that most stars in our galaxy have planets. Now, prior to the test launch, there was a pre-existing orbiting satellite called the Kepler space telescope, and it too was using the transit method to detect exoplanets. And I'm going to show an animation of some of the planets and their some of the stars and their exoplanets, shown here in reference to the solar system in which we live. So this would be our sun, and the third planet out would be the Earth right here. And all of these other solar systems were ones detected by the Kepler space telescope. The planets are shown to be in orbit around their star at the appropriate orbital distances. The color coding here is shown on the left. Planets that have a similar temperature to Earth are shown in blue, and the hot ones are shown in red. So we can clearly see diversity in the solar systems. But ours does stand out. The distances to the planets, the speed of the orbit. Lots of these systems have planets close to the star, orbiting very quickly. The planets are large compared to Earth. As more and more exoplanets are discovered, it stands to reason that more and more will be discovered that have properties similar to the Earth. And that raises, of course, the question whether life may have emerged on those planets.